Inside Microsoft's highly secure facility, scientists were developing a machine that could transform the future of technology. Hidden behind strict security measures, they worked on advanced quantum computers designed to solve problems far beyond normal human capability. But suddenly, the entire project was shut down without any warning or public explanation. Rumors quickly spread about failed experiments, strange discoveries, and unsettling results that may have pushed the project into dangerous territory. Some believe Microsoft uncovered a breakthrough too powerful to manage, while others fear they discovered flaws in quantum systems that could threaten modern technology itself. The billion-dollar quantum gamble began with a simple truth about modern computing. Every phone call, online payment, satellite transmission, digital photograph, and internet search depended on tiny electrical decisions happening inside machines at incredible speed. Traditional computers operated through binary code, where information was stored and processed using bits. Each bit could exist only as a 0 or a 1. This simple concept powered nearly every modern device humanity relied upon, from smartphones to banking systems, from military satellites to entertainment platforms. Classical computing created the digital foundation of modern civilization through endless streams of precise calculations. Classical computers handled problems through structured logic. They evaluated possibilities step by step, or divided tasks among multiple processors working simultaneously. For most daily activities, the system worked brilliantly. Browsing websites, designing buildings, running financial markets, streaming movies, and managing transportation systems all became possible because classical machines could perform billions of operations every second. Yet despite their extraordinary speed, some problems remain almost impossible. Certain calculations involve so many variables and possible combinations that even the world's most advanced supercomputers will require millions, billions, or even trillions of years to process every possible solution. Breaking advanced encryption systems required testing unimaginable numbers of combinations. Predicting molecular behavior for new medicines demanded tracking endless atomic interactions at once. Global shipping networks involved countless changing variables related to weather, fuel, traffic, and timing. Climate prediction became even more difficult because it required massive simulations involving particles, oceans, atmosphere, and energy systems interacting continuously. In situations like these, ordinary computing eventually reached a wall. No matter how fast processors became, brute force calculation alone could not realistically overcome mathematical complexity on such a massive scale. Quantum computing emerged as a possible answer to this limitation. Instead of relying on ordinary electrical logic, quantum machines used the strange laws governing subatomic particles. Rather than bits, they operated with qubits. Unlike normal bits that stayed fixed as either 0 or 1, qubits behaved according to quantum mechanics, allowing information itself to exist in unusual and highly flexible states. This completely changed the framework of computation. Quantum systems no longer process information through rigid electrical pathways alone. Instead, they use the bizarre behavior of physics at the smallest scales of reality. One of the most important principles behind quantum computing was superposition. A regular bit remained firmly locked as either 0 or 1 at any given moment. A qubit, however, could exist in a blend of both states simultaneously until it was measured. This meant quantum systems could represent multiple possibilities at the same time rather than testing each possibility, one after another. By holding many pathways together simultaneously, quantum computers gained potential to explore problem spaces on a scale impossible for traditional machines. The second major principle was entanglement, one of the strangest discoveries ever made in physics. When qubits became entangled, their states connected deeply even across large distances. A change affecting one qubit could instantly influence another through relationships that appeared to violate ordinary intuition. Early scientists found this phenomenon disturbing because it challenged classical ideas about space, communication, and causality. Yet repeated experiments confirmed that entanglement was real. Through entanglement, quantum systems could coordinate information in ways ordinary computers could never naturally reproduce. By combining superposition and entanglement across growing numbers of qubits, quantum computers gained theoretical ability to process extraordinary numbers of possibilities simultaneously. For certain tasks, this was not simply a faster version of existing computing, but an entirely different category of computational power. Properly functioning quantum systems could revolutionize cybersecurity, chemistry, logistics, artificial intelligence, military analysis, and advanced materials science in ways classical systems could not easily match. This possibility triggered one of the most intense technological races in modern history. Governments, corporations, universities, and intelligence agencies all recognize the stakes. Whoever mastered practical quantum computing first could reshape global economic and strategic power. Companies such as Google, IBM, and Intel pursued different approaches to building quantum machines. Microsoft, however, chose a far riskier and more unusual path. Instead of following conventional methods, the company committed itself to an ambitious theory many researchers considered either brilliant or dangerously unrealistic. Although Microsoft was publicly known for software, operating systems, and productivity tools, the company quietly invested enormous resources into deep scientific research. In 2003, Microsoft launched Station Q at the University of California, Santa Barbara. The initiative focused on a bold strategy unlike most competitors. Rather than improving traditional qubits, Microsoft pursued topological quantum computing, an approach rooted in highly abstract mathematics and experimental physics. The attraction of topological systems came from a major weakness in conventional quantum computing: fragility. Ordinary qubits were extremely unstable. Heat, vibration, electromagnetic noise, and even tiny environmental disturbances could destroy delicate quantum states. This problem, known as decoherence, represented one of the greatest barriers in the field. Existing quantum machines required temperatures near absolute zero along with constant correction systems, yet errors still remain common. Scaling such systems into large, useful computers became extraordinarily difficult. Topological qubits appeared to offer a possible solution. Instead of storing information in fragile local states, they aimed to encode data into broader structural properties of a system. Because these topological properties depended on large-scale arrangements rather than tiny local disturbances, they were expected to resist noise naturally. In theory, this could create qubits far more stable and reliable than conventional designs. This revolutionary idea relied heavily on the work of mathematician Alexei Kitaev, whose theories suggested that fault-resistant quantum systems might actually be possible. Microsoft embraced this vision aggressively. If successful, topological qubits could bypass years of engineering struggles faced by competitors. The company believed it might not simply improve quantum hardware, but leap ahead of the entire industry through a fundamentally more durable approach. At the center of this ambitious vision stood a mysterious theoretical particle known as the Majorana fermion, first proposed in 1937 by Italian physicist Ettore Majorana. This unusual particle possessed properties that made it highly attractive for topological quantum systems. The challenge was enormous because Majorana particles had never been definitively observed in nature. Microsoft's entire strategy depended on creating conditions where Majorana-like states could emerge artificially inside specially engineered materials. This transformed Microsoft's project into more than engineering alone. It became an effort involving both technological construction and scientific discovery. For nearly 2 decades, the company poured massive financial and intellectual resources into the pursuit. Elite physicists were recruited, specialized laboratories were created, advanced condensed matter experiments became central to the mission. This was not a side experiment hidden quietly in the background. It was one of the most ambitious long-term technological bets in the company's history. By 2017, excitement around the project intensified. Microsoft began signaling that major breakthroughs were approaching. After years of secrecy, research, and scientific buildup, growing attention focused on facilities, experiments, and claims suggesting that practical topological systems were finally within reach. Expectations spread throughout the scientific community. Investors, researchers, and competitors all watched closely as anticipation grew around what could become one of the most important breakthroughs in modern computing. As Microsoft's quantum ambitions expanded, much of the visible work appeared connected to research institutions, public grants, and university partnerships. Station Q remained the symbolic center of the effort, but the actual research network extended far beyond one location. Building topological systems required highly specialized skills, advanced nanotechnology, and custom materials that only a few institutions on Earth could realistically provide. Among the most important partners was Delft University of Technology in the Netherlands. Delft possessed exceptional expertise in nanoscale engineering, semiconductor fabrication, and experimental condensed matter physics. Researchers there could design and manufacture microscopic structures delicate enough to test Majorana theories directly. For Microsoft, Delft offered not only scientific partnership, but the ability to turn highly abstract equations into physical devices engineered atom by atom. From the outside, the collaboration appeared normal because large technology companies frequently worked alongside universities. Yet observers slowly began noticing that parts of this project seemed unusually secretive compared to typical academic culture. University science traditionally thrived on openness, peer review, conferences, publication, and broad discussion among researchers. Around this particular initiative, however, stronger layers of security reportedly appeared. Silicon Valley companies often relied on secrecy to protect intellectual property, especially when billions of dollars and future market leadership were involved. But some scientists noted that the confidentiality surrounding this project seemed broader than expected. Non-disclosure agreements reportedly extended further than many researchers were comfortable with, and some findings appeared delayed from wider scientific examination for unusually long periods. Then came the publication that seemed to justify years of secrecy and ambition. In 2018, a scientific paper involving researchers connected to both Delft and Microsoft appeared in Nature, one of the most respected journals in the world. Publication in Nature carried enormous significance because the journal's review standards were famously demanding. Acceptance often signaled research considered globally important. The paper carried extraordinary implications because it claimed strong evidence for Majorana fermions within nanoscale systems. For Microsoft's topological strategy, this was not a small detail, but a foundational pillar. If Majorana states truly existed under the reported conditions, they could support the entire vision of stable topological qubits. Years of theoretical work suddenly appear to stand on solid experimental ground. Many observers viewed the publication as one of the most important moments in modern quantum research. But scientific publication was never the final step. Independent replication remained essential. Researchers around the world began attempting to reproduce the results using similar methods and conditions. This process was not hostile. It represented one of the core protections built into science itself. Genuine breakthroughs needed to survive examination outside the original laboratory. Gradually, troubling inconsistencies began to emerge. Experimental outcomes from other researchers did not consistently match what the published paper suggested should occur. Questions appeared regarding measurement interpretation, data processing, and the framing of conclusions. Within condensed matter physics circles, concerns spread quietly at first. The issue was not immediate proof of fraud, but growing uncertainty about whether the celebrated results truly reflected experimental reality. As scrutiny intensified, investigators moved beyond polished graphs and examined raw experimental data directly. This became critically important because published figures often represented process forms of much larger datasets. Scientific integrity depended on whether those process presentations accurately reflected the complete evidence. Over time, deeper examination revealed disturbing issues. Certain choices in data treatment appeared selective in ways that strengthened the desired conclusions while minimizing contradictory signals. By 2021, after extended investigation, Nature formally retracted the paper. Scientific retractions were not automatically devastating because errors happened regularly in difficult research fields. Experiments could fail. Interpretations could overreach. Honest mistakes form part of science's self-correcting process. Yet the situation felt more serious because the central issue involved selective presentation of evidence rather than simple mathematical error. Investigators concluded that certain raw data points inconsistent with stronger claims had been omitted or processed in ways that made results appear more convincing than they truly were. This distinction mattered enormously. The concern shifted away from ordinary scientific uncertainty toward questions about whether ambiguous evidence had been shaped into persuasive certainty. Such concerns struck directly at the foundation of scientific trust. The fallout cast long shadows over Microsoft's topological quantum program. Careers in elite research environments often depended on major discoveries, prestigious publications, and breakthrough results. Within a project carrying global technological significance, pressure became even more intense. Quantum leadership involved not only academic achievement but market dominance, geopolitical influence, and historical legacy. Under such conditions, incentives surrounding borderline results could become dangerously powerful. As conversations widened within the scientific community, more researchers began speaking cautiously about replication problems, internal pressures, and the culture surrounding frontier research. Most did not suggest a coordinated conspiracy. Instead, they describe how extreme ambition, secrecy, financial expectations, and institutional pressure could gradually distort judgment. In highly competitive environments, the line between hope and evidence sometimes became dangerously thin. The collapse of the celebrated paper did not produce dramatic public confessions or explosive announcements from inside the project. Instead, information spread slowly through scientific conferences, private discussions, and investigative journalism. Researchers exchanged concerns quietly. Fragments of information circulated carefully among people close enough to understand the stakes, but cautious enough to avoid direct confrontation. Through scattered conversations, a more troubling picture slowly emerged. Behind Microsoft's polished image of innovation stood a research culture carrying immense expectations. The company had spent years promoting topological quantum computing as a defining long-term strategy. Executives repeatedly reinforced confidence in future breakthroughs. Investors absorbed narratives suggesting that Microsoft possessed a hidden technological advantage capable of eventually outperforming every competing quantum system. As expectations rose higher, pressure intensified inside the program. Failure no longer threatened only scientific embarrassment. It threatened billions of dollars in investment, years of corporate strategy, reputations of elite researchers, and Microsoft's position within one of the most important technological races of the century. In environments shaped by such enormous stakes, uncertainty itself could become dangerous. Rumors surrounding the project grew darker over time. Some outsiders speculated that experiments produced unstable or uncontrollable behavior inside certain quantum systems.